Algebra is a branch of mathematics that deals with solving various kinds of equations. Let's start with a very simple example from elementary school. Suppose we have an equation 3x minus 7 is equal to 5. So how do we solve this equation? Well, we can add 7 to both sides. So we get 3x minus 7 plus 7 is equal to 5 plus 7. And so then on the left we get 3x plus 0. And on the right we get 12. And then this is the same as 3x is equal to 12. And then we get that x, so we take 3x divided by 3 is equal to 12 divided by 3. And we get that x is equal to 4. The word algebra itself is Arabic in origin, and it goes back to Al-Khwarizmi, who wrote a book on Algebra. And basically, algebra is a method of solving equations like this one by moving things from one side of equation to another. And the word algebra means balancing or completion. When we analyze this solution, we see that to solve an equation like this, so we need to use 4 basic arithmetic operations: addition, subtraction, multiplication, and division. And the concept of a field is the axiomatization of these 4 arithmetic operations. So let's give a precise definition of what a field is. Definition. A field F is a set with 2 distinguished elements, 0 and 1, binary operations of addition, denoted by plus, and multiplication, denoted by a dot. Unary operations unary minus, or we will write it as minus x, and also another operation of inversion of non-zero elements, so denoted by x inverse. Satisfying the following axioms. Okay, so before we give the list of axioms, let's discuss this a little bit. So this is our first definition in this course. And in this definition, we use the concept of a set. So what's a set? A set is a collection of any sort of objects. Now, further in this course, we give many more definitions. And actually, when we develop mathematical theory, we build a hierarchy of definitions, theorems, and then more complex theorems, and then more abstract definitions, and so on. But everything must have some sort of foundation, the rock on which our theory is built. And so the concept of a set is one of these foundations or these foundational rocks in mathematics. A set is a concept which is not defined in mathematics. And so basically, mathematics is there to describe the world that surrounds us. And our development of mathematics is guided by the world we live in. And so the concept of a set basically came from the collections of objects that you may carry in your bag. So this is how we understand it. And so we need to start developing theory somewhere. And so set is one of our points of departure. Likewise, the same happens with theorems. So we build more complicated theorems using more elementary and simpler theorems. But there is always a point of departure. So there are certain things that you have to take for granted when you start. And so these foundational truths in mathematics are called axioms. So axioms are things that are not being proved, and then everything else is proved using axioms. Now, another point that I want to make about this definition is that usually in elementary school, subtraction is defined as a binary operation. So what we write often is x minus y. So in this course, we'll take a different point of view. So we will look at this as x plus negative y. So this is how we're defining subtraction. And so here we're using two operations. We use a binary operation of plus, and we use a unary operation of negation. So this operation is applied to a single argument. And finally, so strictly speaking, so these distinguished elements 0 and 1 can be viewed also as operations with no arguments. Well, imagine like in computer science, right? So you can write a procedure that produces a certain output, but has no input to take. All right, so now let us list the axioms of a field. So these axioms will be quite familiar to you because these are elementary properties of the four basic arithmetic operations. So for all x, y, and z in the field F, the following properties must hold. 1. X plus y must equal to y plus x. So this axiom is called commutative law for addition. Then the second axiom is x plus y plus z is equal to x plus y plus z. So this is called associative law for addition. Then next we have x plus 0 is equal to x. So this is axiom of 0. 4. X plus negative x is equal to 0. So this is axiom of opposite. Five. X times y is equal to y times x. So this is commutative law for multiplication. 6. X times y times z is equal to x times y times z. So this is associative law for multiplication. 7. We have x times 1 is equal to x. So this is axiom of unit 1. 8. X times x inverse is equal to 1. Of course, for x different from 0, because inversion is undefined for the 0 element. So this is axiom of inverse. And the last axiom ties together addition and multiplication. So it says x times y plus z is equal to x times y plus x times z. So this is called distributive law. Let me comment on this a little bit. So in this course, we will be working a lot with sets, and often we'll write that certain objects are elements of certain sets. So for this, we have a special notation. So we will write x, y, and z belong to the set F. So this the sign is equivalent to writing that x is in this set. So one may wonder, why did we bother writing down these very well-known axioms? So it turns out that formalizing the concept of a field opens a path to discovering new types of arithmetic. And so these new fields that we will discuss in this course are used in today's technology, in data processing, digital media, and cryptography. And we will talk about this later down the road. Now, let me give you some exercises. Show that in a field if we have x plus y is equal to x plus z, then this implies that y must be equal to z. So this is the first exercise. So the second exercise, show that x times 0 is equal to 0. So the third exercise, show that x times -1 is equal to -x. So what is -1? -1 is the result that we get when we apply negation to 1. And so here it says that the product of x with the negative 1 is the same as applying negation to x. 4. So if x times y is equal to x times z, where x is different from 0, then y is equal to z. And 5. If x times y is equal to 0, then x is equal to 0 or y is equal to 0. All right, so these properties are also quite familiar arithmetic properties. Yet, formally, they are not listed as axioms. So what I'm asking you here is I want you to derive these additional properties from the 9 axioms that are listed here. And what at this point we will be doing is, so in all the calculations in the field, so we will be doing things with baby steps. So this means that when you do a calculation in a field, I ask you to justify every single step by referencing to one of the 9 axioms. Right? So maybe as a warm-up exercise, so you may go back to the example of equation that we solved at the beginning of the class, and then redo this equation, breaking it down to even smaller steps, and justifying every step along the way, every single step along the way, by applying and specifying one of these 9 axioms. So this solution will be longer, but then we will see how these axioms are being used. Of course, we are not going to do this baby step mathematics all the way through undergraduate program, but at the beginning of the algebra course, this is something that I will ask you to do, and this is something useful. Let me show you how to do exercise 5, assuming that you have already done exercises 1 through 4. Okay, so what we're given? So we're given that x times y is equal to 0. And what we need to show is that x is equal to 0 or y is equal to 0. Now let's consider x. Right, so we have the following alternatives for x. So we could have that x could be 0, right? Or we could have that x is not equal to 0. So if x is equal to 0, so case 1, x is equal to 0, so we are done, right? So there is nothing to prove. And so we only have to consider case 2, when x is not equal to 0. But in this case, x inverse exists. So we know that in the field we can take a multiplicative inverse of every non-zero element. So now what we do is we multiply both sides by x inverse. So both sides of this equality. So we have x inverse times x times y is equal to x inverse times 0. Right? So we know this, and so if we multiply this equality by x inverse on the left, then we still have equal expressions. So then on the left-hand side, we apply associative law for multiplication. So associative law for multiplication. And on the right-hand side, we use our previous exercise. I think it was exercise 3. Right? So that said that anything times 0 is equal to 0. So then we get x inverse times x times y. Right? So this is associative law on the left. And on the right, using our exercise 3, we get 0. So next, well, we would like to apply to cancel x and x inverse. But the way how our axiom is stated is we know that x times x inverse is equal to 1. And so thus, to bring it to the form that is stated in the axiom, we have to first use commutative law. So then applying commutative law, we get that x times x inverse times y is equal to 0. So here we use commutative law for multiplication. So now we know that x times x inverse is equal to 1. So we get 1 times y is equal to 0. So this is axiom of inverse. And so after this, well, we would like to say that 1 times y is equal to y. But so the way, again, it is stated in the axiom, it's the other way around. So we have to first use commutative axiom and write that 1 times y is the same as y times 1. And this is equal to 0. So this is, again, commutative law. And finally, we can use the axiom of y, of 1, that y times 1 is equal to y. And we get y is equal to 0. So here we use axiom of 1. All right. So here is an example how we solve a simple problem by breaking it down in many steps. But so the point here is that we can justify every step by referring either to axiom or to some fact that we have already established. And as a result, so we were given that x times y is equal to 0. And in case 1, we have that x is equal to 0. And in case 2, we show that y is equal to 0. And so we were able to demonstrate that given x times y is equal to 0 in the field, then either x is equal to 0 or y is equal to 0. So this property of a field that we proved is an important one. And we will refer to it later down the road. And so here is a piece of terminology. So we say that x and y are divisors of 0 if x is not equal to 0, y is not equal to 0, but x times y is equal to 0. Well, right now this just sounds as strange terminology, but the conclusion that we want to make in this language is that a field has no divisors of 0. So later we will see example of arithmetic systems that will have divisors of 0. And so this exercise tells us that a field has this very nice property that it has no divisors of 0. So this means that if two elements are non-zero, then their product is also non-zero. So in this course, we will encounter some basic simple facts that are important to memorize. And I call such simple facts mantras. And so this is our first mantra, that a field has no divisors of 0. So that's a very simple fact, but it's good to remember this fact because it's useful when we prove more complicated things. Let us now review several sets of numbers that are familiar to us and decide whether they form fields or not. So the first set is, so let's look at integers. And the mathematical notation for integers is z. So these are numbers 0, 1, 2, 3, 4, and also negative, -1, -2, -3, -4. So let's think. Would integers form a field? Well, integers do have distinguished elements 0 and 1 that behave as 0 and 1 are supposed to behave. So then we also have two binary operations of addition and multiplication. We can add two integers and we can multiply two integers. And so now in integers we have also unary minus. So we can take an opposite of every integer and the result is an integer. But unfortunately, in integers we cannot take the inverse, right? So for example, so if we take element 2 and try to consider 2 inverse, right, which is 1/2. So this multiplicative inverse of 2 does not belong to z. And so this means that the set of integers is not closed under multiplicative inversion. Or we can also say that 2 is not invertible in z. So this means that if we look at the equation 2x is equal to 1, then this equation has no solutions with x in z. Now, what is our conclusion here? So our verdict is that z is not a field. Because when we say that a field must have a certain operation, so this means that this set must be closed under this operation. And the set z is not closed under taking multiplicative inverses. All right, so now what can we do to create a field related to z? Well, we can take a larger set. So we can take rational numbers. And the notation for rational numbers is Q. So these are all fractions of the form m over n, where m and n are in z, and denominator n is non-zero. Right. Now let's think whether rational numbers form a field. So here we have 0 and 1 distinguished elements with the required properties. We have two binary operations. We can add rational numbers and we can multiply rational numbers. We can also take opposites of rational numbers. And we can also take inverses, multiplicative inverses of non-zero rational numbers. And from elementary school, we know that all 9 axioms of a field will hold for rational numbers. So the conclusion is that Q is a field. All right, so how about we take a variation of this? So let's take non-negative rational numbers. So we will call this Q plus. So is this a field? So here we can have 0 and 1. And we have two binary operations. We have addition and we have multiplication. Now we have a multiplicative inverse. So if we take a positive fraction, then its multiplicative inverse is again a positive fraction. But the trouble here with this set is that here we cannot take opposites. So because the opposite of a positive number is a negative number, and we excluded negative numbers from this set. And so the verdict is that this is not a field, because it's not closed under unary minus. Next, we can take real numbers. And the mathematical notation for real numbers is R. So here, again, 0 is a real number, 1 is a real number, and we have operation of addition, multiplication on real numbers. We have opposites, so every real number has a real opposite. And also we have multiplicative inverses for non-zero real numbers. And again, all arithmetic properties hold, so this is a field. The next example of a field is foundational for computer science. So this field is called Z2, and as a set, it consists only of two elements, 0 and 1. Now, let's define addition and multiplication of these elements. So for addition, we will say that 0 plus 0 is equal to 0, 0 plus 1 is equal to 1. Now, the interesting thing is that when we take 1 plus 1, well, we have no 2 here, and we declare that this is equal to 0. And because we want to construct a field, so this forces with the commutative law that 1 plus 0 is also going to be a 1, so I'm not going to bother writing this. Now, let's talk about multiplication. So 0 times 0 is equal to 0. 0 times 1 must also be 0 using our previous exercise. And 1 times 1 must be equal to 1. Right? Now, so I claim that with these operations, we will construct a field. Now, remember that field also has unary operations of negation, or taking the opposite, and taking inverses of non-zero elements. But if we define addition and multiplication, then actually the unary operations can be recovered from here. So, for example, well, the opposite of 0 is equal to 0, and the opposite of 1 here. So if we analyze this, so 1 plus 1 is equal to 0. But we also know that 1 plus negative 1 is also equal to 0, right? And so here we can write that 1 plus 1 is equal to 1 plus negative 1. And so then by applying one of our exercises, then we must conclude that 1 must be equal to negative 1. And so if we assume these properties of addition, then we have to postulate that the negative of 1 is equal to 1. And with inverses, well, remember that inverse of 0 is undefined in the field. And so we only need to worry about defining the inverse of 1. But that is clearly equal to 1. So this can be seen from this multiplication property. Now, so what we get is, so this is a field with just 2 elements. So this is the smallest field imaginable. And so this is the foundation of binary arithmetic that is used in our computers. Let's generalize the previous example and consider the set Z7, so which is all possible remainders after division by 7. Well, from elementary school, we know that we can take any integer and divide it by, say, 7 with a remainder. Then what are possible remainders that we could get? So we could get the remainder of 0, right? So if a number is divisible by 7, then the remainder after division by 7 is 0. We could have remainders 1, 2, 3, 4, 5, and 6. And when we divide by 7, the remainder is must be one of these 7 numbers. Now, I want to define addition and multiplication of these remainders. And so basically, to define addition, so to compute x plus y, then add x and y as integers, and then take remainder after division by 7 of the result. And the same for multiplication. So same for x times y. So if we want to define the product of two remainders, then we multiply these remainders as integers and then take the remainder of the result. So, for example, so what do we have if we take 4 times 5? Right. So when we take 4 times 5, when we multiply them as integers, we get 20. And so then our rule says that we need to divide the result by 7 with the remainder. So what is this? So if we divide it by 7 with the remainder, we get 2 times 7, that's 14. So plus 6. And so this means that 6 is the remainder. And so here we're going to write that this is equal to 6, right? Okay, so here we're writing a little bit of a nonsense. We're writing that 20 is equal to 6, and we're going to write a magic word mod 7 to show that here we only talk about remainders after division by 7. So this writing that 20 is equal to 6 mod 7 means that 20 has a remainder of 6 after division by 7. So this gives us the product. So this tells us that in Z7 the product of 4 and 5, 4 times 5 is equal to 6. And okay, so what is 4 plus 5? So 4 plus 5, if we add these as integers, we get 9. But the remainder of 9 after division by 7 is equal to 2. Right? And we write mod 7. So this means that in Z7, 4 plus 5 is equal to 2. Now, the question is this a field? Now, here we have a set with two distinguished elements, 0 and 1, that behave as they are supposed to behave. We have defined operations of addition and multiplication. And the question is, so do we have the other unary operations? So if we have the additive opposites and multiplicative inverses? So with additive opposites, the question is fairly easy to settle, right? So what is the axiom of the opposite? So we must have that x plus negative x is equal to 0, right? So now, for example, if so we take, for example, so take x equals 2 as an example. So the question is, what is minus 2, right? So minus 2 is not explicitly written in this set. But we know that minus 2 must have a property that 2 plus minus 2 must be equal to 0. Now, which element in this set should I take to get 0 as a result of adding to 2? So here we can easily see that 2 plus 5, which is 7 as an integer, but this will have a remainder of 0 after division by 7. So this means that 2 plus 5 in Z7 is equal to 0. And so this tells us that 5 is the negative 2 here in this set. And now we can construct a little table of additive opposites. All right, so let's write a table. So we have x and negative x. And x could have values 0, 1, 2, 3, 4, 5, or 6. Now, what are opposites? So what's the opposite of 0? Well, the opposite of 0 is 0. Now, what's the opposite of 1? So the opposite of 1 is something that's being added to 1 will give us a remainder of 0. And that is clearly a 6, because 1 plus 6 will have remainder of 0 after division by 7. Then we have seen here that the opposite of 2 is 5. And then the opposite of 3 is 4. So 3 plus 4 is again 7, which is 0 mod 7. Then the opposite of 4 is 3. And the opposite of 5 is 2. And the opposite of 6 is equal to 1. So, by the way, so here it's we can see one more fact that we can also list as an exercise. So that if we take opposite of an opposite of x, so this is equal to x, and here we see this in this table. The opposite of 2 is 5, but the opposite of 2 is 2. Right? And likewise for multiplication. So for x not equal to 0, the inverse of x inverse is equal to x. Right? So like prove these two little facts. We also want to construct the table for inverses in Z7. So let's do exactly the same thing, x and x inverse. The only thing that for x inverses, we start not with 0, but with a 1, because the inverse of 0 is undefined. So we only have to worry about 1, 2, 3, 4, 5, and 6. Okay, well, the inverse of 1 is 1. That is easy to see. So then we already defined multiplication. And so our goal is to figure out inversion using multiplication. So how can we do this? So we have the axiom of inverse. So which is x times x inverse is equal to 1. So if we want to find an inverse of an element, then this amounts to solving the equation x times y is equal to 1. So to get that x inverse is equal to y, right? So basically, we will need to be solving the equation x times y is equal to 1. If we can solve, given x, if we can solve it for y, then y is the x inverse. Okay, so let's take the element 2. So this tells us that we are solving 2 times y is equal to 1. Now, of course, in integers, that is impossible to solve. But we are not talking about integers here. We are talking about remainders. So can we find an integer, or one of these, such that when we multiply it by 2 and then take a remainder after division by 7, then the result is equal to 1. And it's not difficult to guess here that if we take 2 times 4, right? So this is equal to 8. But what's the remainder of 8 after division by 7? Well, the remainder of 8 is precisely 1 mod 7. So this tells us that 4 is the inverse of 2, because this is precisely the defining property of an inverse. So a number and its inverse multiplied to 1. And here we have 2 times 4 is equal to 1 in Z7. So this tells us that the remainder of 2 is equal to 4. And for 3, we conclude that the remainder of 4 is equal to 2, because 4 times 2 is also equal to 1. Then, so what is the inverse of 3? So now we need to solve 3 times y is equal to 1. Right? So what integer should we take so that if we multiply 3 times this integer and take the remainder after division by 7, we get 1. And so this integer is equal to 5. So we have 3 times 5, that's 15. But if we divide 15 with the remainder by 7, so it's 2 times 7 plus 1. So the answer is 1 mod 7. So this tells us that the inverse of 3, multiplicative inverse of 3 is 5. And multiplicative inverse of 5 is equal to 3. And so lastly, it's not that difficult to guess that the multiplicative inverse of 6 is equal to 6. Well, one way of seeing this is we can just calculate 6 times 6 is 36. It's 35 plus 1, so the remainder is indeed 1. Another way of seeing this is we can also see that in Z7, 6 is the same as negative 1, right? Well, here we have 6 is negative 1. And in integers, negative 1 inverse is equal to negative 1. So this tells us that in Z7, this property also will hold. And so this tells us that 6 inverse is equal to 6.